Hey everybody, this is example number 3 for Mechanics of Materials covering torsion. The problem statement that we have is the A36 steel shaft shown in the figure below experiences the torque shown. The diameter of the shaft is 30 millimeters and we need to calculate the angle of twist at NB. The shear modulus of elasticity G we can take as 75 gigapascals. So here's our A36 steel shaft. It has concentrated torques acting at location at point B, C, and D. And we need to find the angle of twist at location B, at point B. So the first thing we're going to do is find the internal torques. And to find the internal torques, if we take a look at this figure, we have 3 concentrated torques. So, which tells us that the torques in between, that the internal torque between the concentrated torques will be constant. So we'll take sectional cuts between point B and C, between point C and D, and between A and D. So we're taking sectional cuts between the locations of the concentrated torques to find our internal torques. So first we consider span BC. We took a cut between point B and C. And we take the way I show the internal torque acting at the sectional cut, it's in the positive sense using the right hand rule. And if we sum the torques, we find that the internal torque in span BC is equal to negative 80 Newton meters. Negative 80 Newton meters. Next, we're going to consider span CD and use the same approach. Take a sectional cut and sum the torques. And we find that the internal torque in span CD is equal to negative 60 Newton meters. And again, we consider our last span DA, and we show our internal torque and then the concentrated torques acting on it, and we sum the torques and we find that the span acting in that the internal torque acting in span DA is equal to negative 90 Newton meters. Now that we've calculated the internal torques, we need to calculate the polar moment of inertia that we denote as J. And J is equal to pi over 2 times C to the 4th power. C is the outer radius of the shaft, of the cross-section of the shaft. And so we plug in the numbers. Pi over 2 times our diameter is 0.03 meters. So we divide it by 2 to make it into a radius. And then to the 4th power, our diameter was 30 meters, so that's 0.03 meters. So I calculated J, let me see, I made a spreadsheet for this example that you guys can get at our website at EngineeringExamples.net, and J is equal to 7.95 times 10 to the negative 8. 7.95 times 10 to the negative 8 meters to the 4th power. And lastly, we can calculate the angle of twist at location B. And the formula for this, the angle of twist phi, is equal to the summation of the internal torques multiplied by the span lengths divided by the shear modulus of elasticity times the polar moment of inertia. And we use this summation approach because we're considering multiple spans that have different internal torques. If we just had one span, if the internal torque was constant throughout the shaft, then we would just need one value. But since we have different torque values for different spans, we need a summation approach. So if we take a look at this equation, this summation, we know that the shear modulus of elasticity and the polar moment of inertia, because we have a constant cross-section, J is going to be constant, and because the material is constant, G will also be constant, so we move that outside of the summation just to make things simpler. So now all we're doing is summing the product of the internal torque of each span by the product of the internal torque and the length. So the internal torque for span BC times the length of span BC plus the internal torque of span CD times the length of span CD plus the internal torque in span DA times the length of span DA. We simply plug in the numbers and just make sure you have your units correct. Convert the G into pascals from gigapascals to pascals, and you have this G. This is the This is a G value, and this is J is to the meters to the fourth power, and everything else is Newton and meters inside the parentheses. So our angle of twist is equal to negative 0.019785 radians. Negative 0.019785 radians, which is about equal to negative 1.13 degrees. Negative 1.13 degrees. And so this is the end of this example. Please subscribe to the channel. And again, if you need the spreadsheets, you can access them at our website at EngineeringExamples.net. Thanks.